16:30 or 10:30. Shall we proceed?
Yep, go ahead.
All right. So welcome everybody for the second of Allan MacDonald's 2 lectures. I believe that today he is going to focus on, sorry, I should have started my video. He is going to focus on twisted bilayer graphene and the single particle and in particular interaction physics in this very interesting system. So as this is the second of a 2-lecture series, we will save about 15 minutes at the end for questions. So if you have urgent questions of clarification, put them in the chat. I will see it and interrupt Allan as needed. And otherwise, save your questions for the end. In the question period, again, put your questions into chat, and I will moderate the question session by unmuting people to ask their questions. So with that, take it away, Allan.
Okay. Yeah, so good day, everyone. So today I'm going to talk about another Moire superlattice system, twisted bilayer graphene. And twisted bilayer graphene is especially interesting at certain discrete twist angles where the bands become very flat and correlations become important. So my plan for this lecture is I'm first going to make some remarks about bilayer graphene of the ordinary type, which is this thermodynamically stable structure of AB stack bilayers. For reference, because there's quite a bit or some similarity, at least, between ordinary Bernal bilayers and magic angle systems. Then I'm going to talk about the single particle make some comments about the single particle physics of twisted bilayer graphene. The single particle physics that characterize the nature of the flat bands is what sets the rules for the interactions within those flat bands. The dispersion that remains when the bands are flat, as usual. But the unusual thing about twisted bilayer graphene is that the wave functions of the states within the flat bands are much more non-trivial than in an ordinary flat band system where they are basically the same atomic-like Wannier function on every crystal site. Then I'm going to talk a little bit about broken symmetries, which are very clearly all over the place in these systems, and a little bit about 2 of the very interesting properties. One is orbital magnetism and Chern insulator states that occur in these systems. I'm going to connect that a little bit to linear NT resistivities, a non-Fermi liquid behavior, seemingly, which is commonly observed. Let me start then with AB Bernal stack graphene. So the low energy envelope function Hamiltonian of that system is just a Hamiltonian of a Dirac model with 2 sublattices. That's what I've written down so far for the top layer and for the bottom layer. So those are just 2 ordinary Dirac cones for graphene. And when you have AB stacking, by far the most important coupling between the layers is simply tunneling between the 2 sites that are right above each other in the 2 layers. And these other tunneling between different other sublattices actually vanishes by symmetry at these points. And so you can see if you go to 0 momentum, so this is as usual momentum measured from the Dirac points. And if you go to 0 momentum, These two states that are on neighboring sites are pushed away from the Fermi level by gamma. Gamma's around 0.3 or 0.4 eV, and makes those high energy sites. So when we come to magic angle twisted bilayer graphene, this energy scale will also appear as the energy scale associated with electrons tunneling back and forth between the two layers. But in AB Bernal graphene, the tunneling, sublattice dependent tunneling between the two layers is position independent and has this form. And if you knock out the high energy states, you can see that the these two low energy states are electrons can tunnel between them via the high energy states, but they have to hop twice into the high energy states and back. And when they do that, you get an effective Hamiltonian between these two low energy sites in the two layers. With quadratic rather than linear dispersion. Here wave vector K is Kx minus IKY, and it appears squared here because of hopping twice. So that means that the dispersion of the two touching bands is just normal quadratic dispersion, but the wave functions are unusual because the tunneling matrix element depends on direction of momentum. And right. So when I express that Hamiltonian of bilayer graphene in terms of Pauli matrices that represent tunneling between the two low energy sites, which are now on different layers. There are two bands. But if I express it in terms of Pauli matrices and think of these states in terms of a block sphere in this formed by this two-level system for each K, which is the two low energy sites in the two layers, then you can see that the eigenstate, let's say in the conduction band, the positive energy state will be on this block sphere will be pointing in the same direction as this effective magnetic field if you view these as a pseudospin. And in particular, the state will wind around lines of constant latitude, if you like, twice when you go around a circle in momentum space. And so it's natural, so this, it turns out this, whoops, I'm off screen here. Turns out that this property is not very favorable from the point of view of electron-electron interactions, because if you view this state as a pseudospin, then you have states that are changing their pseudospin very rapidly as a function of momentum, and exchange energies are always lowest when, just like in a simple ferromagnet, when all states have similar pseudospin. So in this case, you can look for broken symmetry states in which there's spontaneous polarization where you move off of move the states off the equator of this Bloch sphere, and this self energy here induces spontaneous layer polarization. So you could do a mean field theory, and you can ask yourself whether you can get a self-consistent state which spontaneously breaks layer polarization and generates a self-energy proportional to sigma z. And for that, we can write down the Hartree-Fock Hamiltonian for this system in terms of interactions between different momentum states. And the Hartree-Fock operator is basically projection onto these states. And if I use for a spin-a-half coherent state the following expression for projector operator, let's call this valence band occupied. And this is the operator for projection onto this valence band state. So if you go through that, you get a mean field expression, self-consistent expression for lambda induced by interactions, which is in the case where this interaction here, for example, is just a constant delta function interaction, you get a BCS-like expression. Where nu naught is the constant density of states corresponding to the parabolic single particle band. And this integral is only correct up to scale of the low energy states, which is gamma. So just like this looks exactly, of course, like the gap equation in BCS theory. And so in a mean field theory, you always get broken symmetry states in magic angle, in bilayer, twisted bilayer graphene, where you have spontaneous layer polarization. And so far, I've ignored, oops, let me put this back. So something similar happens in single layer graphene. In which there's spontaneous sublattice polarization if interactions are strong enough. For delta function interactions and quadratic dispersion of the bilayer, in principle, you get broken symmetry states for arbitrarily weak interactions, but turns out that in single layer graphene, something very similar happens as long as this effective fine structure constant of graphene is big enough. So the effective fine structure constant in single layer graphene to get these broken symmetry states has to be bigger than in mean field estimate has to be bigger than, maybe 1.5 or something like that. Uh, 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 in order to really estimate what the necessary interaction strength is in single layer graphene, you have to do a serious calculation. And over the years, I've talked to people trying to do um, uh, quantum Monte Carlo calculations of different types, but I don't think anybody really has a number for this. But for a Dirac system, the expectation is if the velocity was small enough, or if the interaction, one of our interaction strengths were large enough, then even in single layer graphene, you get a spontaneous sublattice polarization, which opens up an energy gap. And okay. We know experimentally, I think pretty well, that broken symmetry doesn't occur in single layer graphene, but in bilayer graphene, there actually is evidence that it does. Okay, sorry about that. Am I still here, Andy?
I need to unmute me. Yes, I can see you, but we don't see your screen. There we go.
Okay, sorry about that. I don't know what happened. We practiced before and it worked. So I'm trying to switch back and forth between different apps, which I didn't do successfully. But this is a theory calculation for Bernal bilayer graphene of different insulating states that occur as a function of, along the x-axis, this is density measured in units of filling factor, because this is done in a weak magnetic field, but a very weak magnetic, in a non-zero magnetic field, but a very weak magnetic field. So filling factor along this axis, and gate voltage along this axis. And the thing I haven't mentioned so far is in bilayer graphene, of course, all of the bands occur with 2 valleys and 2 spin states, so 4 flavors. And so you can have a sense of layer polarization for each of those 4 flavors. It should be obvious from my block sphere picture that I drew, and the relationship between Berry curvature and area covered on the block sphere in a 2-level system, that all of these states have non-zero Berry curvatures that integrate to equivalent to covering an entire sphere if you integrate over momentum space. So they give Hall conductivities of 1. And but it seems to be a preference for states in which opposite valleys have the same sense of layer polarization. And that means that they have actually opposite Hall conductivities by time reversal symmetry. But the point is that there are other states very nearby in energy that can be stabilized by magnetic fields, which do have a non-zero Hall conductivity. It's been noticed a long time ago that some quantum Hall effects occur at extremely low magnetic fields in high quality bilayer graphene. And indeed, we believe that some of these stable quantum Hall effects are basically these quantum anomalous Hall states that are created, for example, when you make opposite valleys have opposite sense of layer polarization, specifically in bilayer graphene. And so these are states, you can choose, by choosing the sense of layer polarization, you choose a Hall conductivity for each flavor. This nu equals 0 axis in this phase diagram has been heavily explored experimentally by many people, and there's always an insulating state at no gate voltage, and then a region which is not very insulating, and then another insulating regime. And this is generally understood as a transition between an antiferromagnetic state, which is the ground state at no gate voltage, and a layer polarized state for large gate voltage. But all of these states are gapped, and they're basically like the mean field states I was just describing. And if you choose the sense of relationship between valley and layer polarization in different ways, you get states with non-zero total quantized Hall conductivity, including states with Hall conductivity 2, which appear at filling factor 2, and Hall conductivity 4, which appear at filling factor 4. And indeed, there's good evidence from some experiment that reasonably good evidence that these states occur. So let me see if I succeed in going back to my other screen. Okay, hang on just a sec. Okay, am I there?
I see you in one little window, and I see a blank screen, which is a visualizer, the white sheet of paper that you could write on.
Yeah, okay, very good. Okay, so I guess now I'm going to switch to magic angle twisted bilayer graphene, and I'm going to say that the physics that occurs there and is much more robust in magic angle twisted bilayer graphene is similar but more robust than what occurs in AB Bernal bilayer graphene. Okay, so what is the Hamiltonian of twisted bilayer graphene? So this can be derived in the same way as exactly the same spirit as I employed last time for the TMDs, just like in the case of AB bilayer graphene. there are two layers in which there are hopping among the graphene sheet pi orbitals, which at low energy is represented by this Dirac model. But now with the Moiré pattern, there is sublattice dependent tunneling between the two layers. Each layer has two sublattices, and so this is tunneling from, or hopping from layer B to layer A. Before, this tunneling block, interlayer tunneling block, was a constant independent of position and had just one non-zero entry. When we changed the stacking, this 2x2 matrix is a function of position. I was going to step you through some steps in deriving that, and I may refer to one detail in a moment, but let me just say that it's exactly derived in exactly the same spirit as I talked about yesterday. And it gives this result. So the tunneling is position dependent. I'm just going to write down here chi is 2 pi over 3. The scale of this is the same scale that gives write down one more. I'll write down, so there's one element. TBA is not the complex conjugate of TAB. I guess in the notation I used before, this should be TBA. So you can see with chi equal 2 pi over 3, r equals 0 is, we'll give TAA equals 0. This is, for r equals 0, this is 1 plus twice cos 2 pi over 3, which is 0. And that's because I've chosen the origin of coordinates for writing this down to be local AB stacking between the bilayer. So TAA is 0, TBA BA is 0, and so you have this position-dependent stacking. And so that gives you, when you apply those two things together, you get magic angles. One thing you can easily see, you can see that in momentum space, what this position-dependent hopping does, of course, is for a given k in one layer, it's coupled to a different k in the other layer, differ by one of these three momenta, which are actually have the same magnitude. Have the same magnitude, and they have relative orientations of 120 degrees. So for example, the Dirac point of one layer is coupled at first order, directly coupled to points at the other layer, and here I'm measuring momenta in both layers from their Dirac points, at momenta at three different momenta, that are Q1, Q2, and Q3 away from the Dirac point. And so if I just try to get an approximate understanding of what's going on, then I can write down a 8x8 Hamiltonian with two-dimensional blocks for the two sublattices in each layer, phi naught for the momentum that's near the Dirac point in one layer, and three other two-component spinners, sublattice spinners near different momenta at the other layer. And so if I look at this, for example, at the Dirac point, where the Hamiltonian in this block goes to 0, I can see that to get 0 energy states, I need that, Hi on psi I is sorry. But I look at the first component here, Ti on psi I is Hi on psi naught. So the, let me see. Sorry, I did this wrong. Hi here is, this is the Dirac Hamiltonian at the momentum this is coupled to. So this is basically just doing, first order perturbation theory in this space, and you can write down how the wave function of the Dirac point in one layer is changed by its coupling to the other layer. And if you calculate the expectation value of the velocity operator in that perturbed state, then you get a reduction in velocity, which is proportional to the ratio of the coupling strength to the difference of kinetic energy of these Dirac points. And it says the velocity goes to 0 at a certain value of alpha. So that's kind of the first hint that there's a magic value where the velocity goes to 0 and the bands become very flat. I'm going to skip what I was going to say about the limitations of this model. There are certain ways in which we know this model is inaccurate that can easily be improved. Some of these ways have been implemented, and sometimes are implemented and sometimes are not, and may or may not be important for what goes on. But let me write down, here's another way to look at the flat bands, another simple way to look at the flat bands. Okay. This is looking at a particular point in momentum space. If I have if I go back to this picture, whoops. Let me go over here. So we're interested in the states at the Brouin zone corner, and if I rotate this Dirac sphere by a little bit, then I have the other layer has a Brouin zone that goes like this, and I'm going to look at the point which is just halfway between the Dirac point of one layer and the Dirac point of another layer. And so this is the y direction in the coordinate system we usually use. So this here, I've just taken a cut of the uncoupled layer dispersion along a line, along this line. And at the point in momentum space, halfway in between, when the layers are not coupled, there are four states. They're both far away from the Fermi level. They're far away by this energy scale, the interlayer coupling energy scale, which is, depending how you normalize things, you know, something around a couple of 100 millielectron volts. And I'll come back to that scale later. At this point in momentum space, you can see that one of the single layer states has moved in one direction relative to its Dirac point, and the other has moved in its other direction along the y direction. And and they both move by half of the distance between these two Dirac points, which is the magnitude of this momentum boost Q, which is the product of the magnitude of the wave vector at the Brouin zone corner times the twist angle. And so the Hamiltonian there, single particle Hamiltonian in this model is, you know, it's the Dirac cones of the two layers. For single layer graphene, because the off-diagonal matrix elements in the Hamiltonian are kx minus iky, in the y direction, you know, the Hamiltonian is purely imaginary, y direction of momentum space measured from the Dirac point. So this is in sublattice space, this is a y Pauli Hamiltonian. And it's opposite in the two layers because I go in opposite directions to this midpoint from the two layers. And then I have tunneling between the two layers. And it turns out that that for this momentum, you can show that the sublattice dependence of the interlayer tunneling has a part that is diagonal in sublattice. So this is sigma operators act on sublattice, tau operators act on layer. So this is an interlayer tunneling term in the Hamiltonian that's sublattice independent. And I call this the parameter of that W naught here, W1 sigma x tau x. Okay. So that's a 4x4 Hamiltonian. W1, of course, this is, I'm using index 1 for tunneling amplitude between sublattice, between layers. And the reason I separate these coefficients, W0, W1, is connected to one of the important corrections to the simple model. And that is we know that tunneling there are effects that reduce the tunneling on within the same sublattice somewhat compared to tunneling between different sublattices. And maybe this ratio is 0.8. The simplest way to think about that is that it's known that when the local stacking is AA, then so the tunneling then is mainly between the sublattices, then the layers actually move farther apart from each other, and that reduces the strength of that tunneling. But anyway, this 4x4 Hamiltonian, you can diagonalize exactly. I won't step through the details. It turns out that the energies are, 4 energies are given by this expression. Vg is the Dirac velocity. And so of these 4 energies, 2 have low energy. And so this is like AB Bernal bilayer graphene, where we started off with a 4x4 Hamiltonian, but then there was a low energy space within which we examined the effect of interactions. Same is going on with bilayer graphene, twisted bilayer graphene. You want, when both of these terms are approximately equal in magnitude, you notice actually at this point, if W0 equals W1, as you get level repulsion between these levels, pushing 2 of them towards 0, for W0 equal W1, they actually never exactly touch. But for W0 less than W1, they can actually cross. But you can see here the flat band condition anyway is when these 2 terms are the same. And this occurs at nearly the same point that the velocity goes to 0. And in order to have these, in these low energy states, there are non-trivial correlations, just as in the AB Bernal bilayer graphene case. The low energy states were one particular sublattice in one layer, one particular sublattice in the other layer. In this case, there is a correlation. So let's say this magnitude is roughly the same as these magnitudes. Let's say if I just simplify things by ignoring the intra-sublattice tunneling, you can see there's a correlation between the sublattice dependence of the wave function, sublattice coherence in different layers, and this tau z is basically sublattice coherence within a given layer. So there's a particular, more complicated form of 4-component wave function that's in the low energy states. And one of the complications is that this nature of this correlation actually changes with momentum in the Moiré-Bruin zone. And that's a complication, although in much of the Bruin zone, it's similar. So, okay. What was I going to talk about next? Okay. So just like Bernal bilayer graphene, am I back?
Sorry, I keep having to unmute. Yes, yeah. You are back.
Okay, so that worked smoothly, more smoothly. I don't know what I did differently. So this is, these are the magic angle flat bands in bilayer graphene. It's quite impressive if you compare the overall energy scale, what you typically get if you just took energy scales divided by momentum scales, you get velocities around 10 to the 6 meters per second, which you have at larger angles. And then all of a sudden you get these extremely small velocities. And this slide is emphasizing one of the very important complications, which is in understanding interaction effects inside these very flat bands. And it's the fact that the wave functions aren't the same throughout the Bruin zone, and how that impacts interactions. So what I'm showing here in black is some version of the of the single particle flat bands that I showed you previously. And what I'm showing in blue is the flat bands that you get if you just include interactions at a mean field level with the flat band completely empty, so no correlations at all. And there are various things reflected in here, but the simplest one to talk about is that when the flat bands are empty, the charge density, because the flat bands are actually, turns out their densities peak near the AA points in the Moiré pattern. When they're empty, there is a hole in the density near AA points, which is attractive for electrons, and the wave functions near the center of the Brouin zone, Moiré-Brouin zone, labeled gamma here, they have less weight in this attractive region in the potential. And so in relative terms, they get shifted up. So, you know, in the non-interacting bands, it turns out that the bottom of the flat band is, you need to blow it up here to see it, but it's always at this gamma point in the Brouin zone. But here, it actually, if you look at the valence band, when the valence band is empty, it's actually, in this calculation, the top of the valence band. And so that's a complication that hasn't been sorted out yet in terms of how it influences observables. So that's a detail I wanted to mention. But what happens to the you know, one of the main physical properties that's observed is that they're insulating states all over the place. The bare bands never have gaps, but they're insulating states seen, and that's normally associated with just the sublattice symmetry breaking that I told you about in twisted bilayer graphene. And the simplest way to think about that as a function of twist angle is, I mentioned in single layer graphene in a Hartree-Fock theory, there's a criterion in terms of fine structure constant for you know, when you break this symmetry and open up a gap. And this line is where Hartree-Fock theory would say, you know, where that instability would occur if the only correction I included was that the velocity was renormalized to make a smaller velocity and a larger fine structure constant. So if you actually do Hartree-Fock calculations, as in this paper published in PRL, it turns out that because the wave functions are more complicated, that instability to a gap state occurs you know, at this interaction strength. Of course, we expect that the mean field theory will overestimate this instability. And as I said, even in the simple case of bilayer graphene, we don't know really where it occurs, but we can expect it somewhere up here. And this is largely consistent with experiment, and some of which show gap states at neutrality. This is at neutrality, like in bilayer graphene, and some do not. But generally speaking, when you are at neutrality, in other words, when the valence band is filled but the conduction band is empty, then you have an insulating state. And let me go back, see if I can go back now. Press the right button this time. Okay, that worked better. So generally at neutrality, just like in bilayer graphene, like Bernal bilayer graphene, probably their state is normally gapped, and among these gap states, you can have ones which have no Hall conductivity, no net Hall conductivity. When you form these gap states, it turns out that they all have a Chern number at neutrality. And just like AB Bernal graphene, that Chern number depends on the sense of lattice polarization or sublattice polarization in the generalized sense I was trying to hint at when I gave you the example of the wave functions at the point halfway between the two Dirac points before. There are two of those low energy states, and the sign of the Hall conductivity depends on, loosely speaking, which one you pick. And so there are lots of competing states. And when we include the fact that there are 4 flavors, including spin and valley, by assigning the sense of this this C2 or Z2 sublattice symmetry breaking to each of the flavors, that gives us 2 to the 4, 16 different states, some of which have Hall conductivity 0. These are likely the most stable, but there probably are nearby states with Hall conductivities 2 and 4, just like in the bilayer states, and it would be very interesting to see in the fullness of time of if these can be stabilized by weak magnetic fields, like in the AB Bernal bilayer case. But there is an important difference between the AB Bernal bilayer case and the Moiré superlattice case. Here I'm going to sketch as a line sort of a gap state in AB Bernal bilayer graphene. If I break the layer symmetry or some sublattice symmetry, I can open up a gap, and the size of that gap might be fairly small, but you can open it up. And the difference, if I can do this in dashed lines, is that if I open up a gap in the Moiré superlattice system, first of all, the density of states is bigger because the bands are flatter. But the most important thing is that the conduction band and the valence bands are each separated up into a bunch of Moiré mini bands. By single particle physics. And we can hope that, we usually think, just like we do in fractional quantum Hall effect, where we ignore Landau level mixing, that we can ignore these remote bands and just concentrate on correlations within this finite energy width flat band. And what that does is it opens up the possibility of having, for some of the flavors, having the valence band filled and the conduction band empty, so that you're for that flavor at neutrality. While the flat band might be completely full or completely empty for some of the other flavors. So that gives actually a richer state set of possibilities. So for example, let me take for nu equal -1, for example. And here I'm measuring filling factor in these Moiré superlattice systems in terms of number of electrons or holes per Moiré unit cell. So nu equal -1 means that the number of electrons is sufficient, number of holes is sufficient to empty one band. And if you break the flavor symmetries. And as I'll show you, there's very clear experimental evidence that this usually occurs. And you would just occupy 3 of the 4 valence bands. And so now you have 3 valence bands to pick a sense of sublattice polarization. And the Hall conductivity, depending on how you break that symmetry, if you get 2 positive Hall conductivity and 1 negative, then the total Hall conductivity would be 1. If you pick them all to have the same Hall conductivity, probably these are higher energy states that would have to be stabilized by a magnetic field. Then you can get a Hall conductivity of 3. And so this appears to be a part of what's going on. And in particular, if you have filling factor -3 or +3, you only have 1 empty or 1 whole band. And yeah, you only have 1 empty or 1 whole band. And so the Hall conductivity is 1. There are 2 states with a given sign of Hall conductivity, we expect, and that differ by the sense of this broken sublattice symmetry. And so the quantum anomalous Hall effect experimentally is usually observed when you put the magic angle twisted bilayer graphene on boron nitride, which explicitly breaks the sublattice symmetry and picks a state. So that's, I think I need to stop there. So let me go on to the next thing.
Right, so Alan, this is a good moment to say it's 11:27. So in our normal timing, there's sort of 18 minutes.
Yeah.
Okay, thanks.
Okay, so let me talk. We expect and has been observed experimentally in some cases that churn insulators are common in as ground states in magic angle bilayer graphene. Basically, in this kind of picture I've been outlining, an insulator has to be a churn insulator if the Moire band filling is odd. And we'll see whether or not that's always true. And I want to talk a little bit, I want to say one thing about the interesting properties of these churn insulators. Last time, or when he's in his Tuesday, I think it was, lecture, Leon mentioned the Strata formula. So Strata formula is always dear to my heart, in part because I first met Pavel Strata completely by accident in a train car going from Venice to Trieste in the summer of 1982. We were actually going there to work with each other, but we didn't know each other, and we accidentally discovered each other in that way. So Strata formula says, says that the when you have a churn insulator, the electron density below the gap depends on magnetic field, which is connected, which Leon explained last time. So here I'm writing the Hall conductivity as an integer, Hall conductivity in units of E squared over H. So this is also the total churn number. And you can write the formula that, for the Strata formula that Leon derived last time in terms of the Chern number, or integer Hall conductivity, dimensionless Hall conductivity, area, and magnetic flux quantum. And so dNdB is, of course, N. I'm just going to write down a thermodynamic expression for dNdB. N is in a derivative of the thermodynamic potential with respect to chemical potential. And if I do this if I use a Maxwell relation and take the derivative the other way, you can see it's exactly the same as the derivative of the magnetization with respect to chemical potential. And that means that one unusual property of these systems, if you think of them as magnets, is that the magnetization jumps as a function of carrier density. And the change of magnetization when I go across the gap, if I just copy down this formula, Schrader formula for the NdB, is related to the energy gap. So this formula gives you a scale for the orbital magnetization. But also because all of these systems have some kind of approximate particle-hole symmetry, we can expect the magnetization typically to have a small value. And so this jump in magnetization should be the same scale as the magnetization, and it's probably larger than the average magnetization typically on the two sides of the gap. So this says I have an insulating magnet, and in a given magnetic state, the sign of the magnetization in this insulator depends on whether I dope it N-type or P-type. So how big is this magnetization? And if we want to compare it, if we want to compare it with the orbital magnetization, if we want to compare it with spin magnetization, let's say, so this is magnetization per area times the A sub m here I'm using to stand for the area of the Moiré unit cell. And so we're used to writing this, magnetization per period of a periodic system in units of Bohr magnetons. For a spin magnet, this is, some number of Bohr magnetons. So let me multiply and divide by Bohr magneton and put down the explicit expression for the fine structure constant. I'm at CGS forever here, so you can see that this magnetization, if I express it in units of Bohr magnetons per unit cell, it's of order of, energy gap divided by h bar squared over 2n A Moiré. This is actually the kinetic energy scale associated with Moiré superlattices that Leon talked about on Tuesday. And in bilayer graphene, there's energy gaps. The Coulomb energy scale is much bigger than the Moiré, than this kinetic energy scale associated with the Moiré band. So in principle, this can be, quite a bit bigger than 1. I'll put much, but maybe not very much. This is, there might be some spin magnetization as well, and So this orbital magnetization is typically the larger magnetization, and it has this interesting property. And I think did I successfully change that time? Andy?
I'm still muted. That's better. I was muted.
Yeah.
Basically, all I can see is a little horizontal bar of the top of your PowerPoint slide. So you changed, but what you've changed to is not, it just says lecture supplementary slides, PowerPoint as a little bar. There we go. Now
Okay, that one worked. Okay.
Yep, now it's good.
Good.
Thank you.
Good. Okay, so yeah. So I just wanted to show you this beautiful experimental result from the group of Andre Young, this recent preprint. What you're seeing there is looking at densities near an insulating state. It's actually nu equal +3 for HBN on boron nitride. And you see what he's measuring is the Hall conductivity as a function of gate voltage. So for a given sign of magnetization, what's happening is that the magnetization of a given state changes sign, but the state that the state that's selected is the state with the sign of magnetization that lines up with magnetic field. So this voltage changes which of the two competing states is lower in energy. It changes the energy curve, let's say, of usual order parameter in a symmetry breaking field, in this case, the magnetic field. By changing doping, you change from this to this. And you change state, and it turns out that the Hall conductivity does not change sign across the gap. So you get this very interesting behavior, which proves experimentally that this is dominantly an orbital churn insulator. Let me stick with this for a bit, since the efficiency of the interchanges is not 100%. One of the key issues in understanding the experimental observations, and I think understanding of this is coming along, and we're really getting there, is where are the flavor symmetries broken, and how are they broken? And this particular curve is a theoretical unrestricted Hartree-Fock calculation with 4 flavors, and allowing the flavor symmetry to be broken down to two equivalent, 2 different from other 2 to 1 different from the other 3, let's say, or allowing all to be different. And in this mean field calculation, if you start from neutrality and start to empty the valence band, then for a little while, no flavor symmetries are broken. That's kind of consistent with experiment. In these mean field calculations, it depends on the interaction strength you use, but usually you get insulating states at all odd filling factors, all of which have a non-zero total churn number. Near filling factor -2, two flavors are different from other 2 flavors. There's good reason to expect the stable thermodynamic state has Hall conductivity 0. But when you approach -3, you break that flavor symmetry again. So those kinds of flavor symmetry breakings near integer filling factors are seen in experiment. This is an example. This is just the derivative of that energy curve I showed you to get a chemical potential. This is so chemical potential as a function of filling power. The blue curve is allowing all symmetries to be broken. And often that's what's seen experimentally. In this particular curve from Allan et al., there are many other people with similar data. They only see insulating states at neutrality and at these at the filling factors plus and minus 2. Another very interesting observation that I think is going to tell us a lot, and there's lots of data on this from lots of different people, but I think there's more data to gather, and that's looking at the carrier density as measured from the weak field Hall effect, so-called Hall density. This is a typical measurement. The density of holes as measured by the Hall effect is just the density of holes that you would get from electron counting as you start from filling factor 0, and then it resets to 0. And so this reset is almost certainly associated with simply emptying the valence bands for 2 of the 4 flavors. And the fact that the Hall density reset from 0 starts emptying again says that the Fermi surfaces of those other flavors do not return. In other words, these flavor symmetries are broken throughout the insulating state, and in particular in the regime where we have superconductivity. And let me, since I'm running out of time, so anyway, there's a lot to understand in this Hall data, and I think it's actually very important. Let me turn to another important experimental observation, and this widely observed. This is a summary from Andrea Young's group, and they look at the resistivity as a function of temperature. Away from the magic angle, you see some typical 2D conductor behavior. At the magic angle, you see, just like in cuprates, a large linear in T resistivity. And this occurs, this large linear in T resistivity occurs over a very broad range of band filling and over a range of twist angles near the magic angle. So it's a very generic phenomenon. And there is a explanation, possible explanation for this in terms of phonons, and that explanation does not hold up. And when you include, the rationale for the linear in T resistivity from phonons, of course, is what you see in every metal above the Debye temperature. And the rationale is that in the Moiré flat band, the Fermi surfaces are small, and so only small Q phonons can induce transitions on this small Fermi surface within the Moiré miniband. But in fact, large Q phonons, when you include the fact that these wave functions in the flat bands are not plane waves, then you can excite, then transitions between them can be excited by large Q phonons. And this is for some band structure model. One of the lessons of my talk is there maybe is some uncertainty of what the right band structure model is when you include interaction dressings in particular. But except for very close to the neutrality Dirac point, the resistivity that you calculate from phonons is much smaller and is not a linear function of temperature. So I don't think that's what people are seeing over a very, very broad range of band filling factors and near the magic angle. And I'm just going to end with a speculation. And the speculation is that maybe this is maybe these collective modes I'm showing in this plot are what is producing the large linear in T resistivity. So what are these collective modes? This is actually a calculation for the particular case of filling factor -3 or -3/4, as it's denoted on this graph. Only one electron per 3 holes per Moire unit cell, so one valence band filled. And basically you have collective modes from transitions between that occupied flavor and all of the empty flavors. And so this this calculation is actually a time-dependent mean field calculation. It's sort of, you can think of it as the equivalent of, sort of spin wave theory, but it includes all of the fermionic physics and is unabashed about, unbiased about what the localized degrees of freedom are in the flat band. And so there are several things to say about these results. One thing is that the energies of these modes, which is an EV or 2 in this plot, is way below the single particle gap of these insulators. And so these are light spin waves. They're something that is a neutral excitation, a neutral particle hole excitation. Exists everywhere throughout the Moire flatband-Brouin zone. And each of these can be associated with transitions between different local degrees of freedom. I'll explain more in just a second. So the number of modes here is exactly the number we expect. And there are no extra modes at higher energies. So what this means is that the only low energy neutral excitations below the particle hole continuum, at least in these calculations, are local excitations, some change in the state of the electron within each Moire unit cell. So the electron wants, in this case, 1 electron per Moire unit cell, but it cares much less what that 1 electron state is. And what these 1 electron states are basically a SU8 degree of freedom, SU2 cross SU2 cross SU2 for spin and valley, which you might expect, but also for this sublattice degree of freedom within the lowest Landau level. The 2 somewhat complicated things in this case that are being brought down to low energies. And so I think that there's robust low energy physics that has nothing to do with fermionic quasiparticles in the insulating states. And some of these modes are actually associated with the fact, not associated with breaking any flavor symmetries. They're just associated with this generalized sublattice degree of freedom I've been talking about, and labeled here as exotonic excitation. You can think of it as a low, a bound state of interband excitation, although it's probably not the right way to think of it. Those are present even with no flavor symmetries are broken. In our calculations, they're present even in the metallic states. And so they may be a bosonic degree of freedom that's present that the electrons can scatter off. And you can see that the energies of these excitations only go up to an EV or 2. And so this robust soup of low energy local excitations is probably, I believe, what's producing the linear T resistivity. And if God is kind, maybe this is what's producing the superconductivity as well. So let me stop there and turn it over to you, Andy.
All right, thank you very much, Allan, for this very interesting set of talks. So let me ask the audience there, if there are questions, please put them in the chat window, and I will convey them to Allan. And while people are thinking about this, um, concerning the linear resistivity, of course, how low in temperature should this go? Because of course there are 2 points. The collective modes have gaps, and the ones that don't have gaps, the massless point is at k equals 0, raising momentum conservation kind of questions.
Yeah, so that is, it's interesting to look at the data. I'm not sure if I have anything here, but it doesn't go to 0 temperature in this picture.
Right.
You know, as you very well appreciate, Andy, you know, thinking about what these collective modes are like in the metallic state is a complicated question, but they certainly have lower energy in the metallic state. And so, you know, one of the key questions here is how do these collective modes interact with the low energy excitations around the Fermi surfaces, around the Fermi surface. You know, maybe it's like a ferromagnetic metal where the collective excitations always have a small gap, a little gap that keeps you out of trouble at low energies. And if the important excitation is this exotonic one, then that will that will always be gapped. So, but probably in this theory, or at least in any theory we can actually do, that this linear in T resistivity doesn't go down to 0 temperature. And so that could be a very fundamental, you know, experiment ultimately of really testing as well as one can experimentally how far the linear in T resistivity behavior goes down.
So,
I'm not sure if I'm completely up on all the experimental facts on that.
Yeah, well, given the way the field is moving, I don't know that anybody can be. Sorry, related to that, there's an interesting. Well, you know, I'm saying things that you know, but there's 2 interesting features of a linear resistivity. One is the slope, and the other is an intercept.
Right.
Right. You know, and one possibility is that an intercept is just disorder, and there's some kind of Matheson's rule that's simply, you know, taking intrinsic behavior and shifting it up.
Right.
But the other possibility is that it's associated with some sort of physics of the modes. I mean, phonons typically have a linear resistivity with a non-zero intercept, and you learn something about characteristic frequencies from that intercept. You know, the curve eventually has kind of like an S.
It doesn't go linear to 0 temperature, you mean?
Yeah, eventually there's some kind of downturn. And the point is that you can infer something about that from the high temperature extrapolated intercept.
Okay, yeah.
So,
yeah, so
anyway, this was just, of course, disorder is the other
yeah, and you know, I remember having conversations with different people at different times about, you know, there are many examples where this linear in T resistivity has been highlighted, you know, in recent years in the literature. And very often the linear, you know, the extrapolated value for the resistivity at 0 temperature corresponds to very long mean-free path. And you know, so that means, I guess, that the transport theory is under good control if there's a long mean-free path, but you still have to explain how you get linear in T resistivity. I think that most of this data extrapolates to not extremely large mean-free paths when measured in the relevant unit for these crystals, which is the Moire length.
Yeah. So
yeah, we can see a resistivity on that plot of, you know, 1 kilo ohm. So that's, I guess, KFL around 1020 or something like that.
Yeah. Yeah. Interesting. All right. So I still don't see any questions in the chat window, so I'm going to take advantage of the opportunity to ask you a couple of more general questions.
Okay.
You sort of alluded to this in your talk, but there's been a lot of discussion, particularly from people coming from the DFT community, about lattice distortion effects substantially changing the band structure and changing the interactions and leading to a substantial electron phonon interaction. You know, you mentioned essentially that the hopping and therefore the bands can be modulated between AA and AB. Anyway, what's your view of that? How should we think about the importance of electron lattice interactions in these systems?
Well, you know, as I mentioned yesterday,
Yeah.
the interaction with the lattice produces strain effects, which introduce a new length scale. So
Yeah.
The Moiré period's not the only length scale. And you don't have, you know, these, that creates new physics, which means, you know, you can't describe all twist angles in terms of the same parameter.
Mm-hmm.
But, you know, fundamentally all it does, though, I think, is it just changes the periodic potential from one thing to another thing. And so I think the more important point, you know, that this length scale is basically a stacking fault grain boundary, type grain boundary. And its width is determined by, you know, well understood parameters, and its values are known in these different crystals. And I think when you have, you know, so when the Moiré periods are very long, or this domain wall width length is very short, then you can view the periodic system as simply, you know, a periodic array of stacking boundary stacking changes that intersect at certain points. But I think that the main point is that if those are strong, they'll tend to get pinned by inhomogeneities in the system. And I think from a practical point of view, even though ideally you should just have some different periodic potential, then this will make all of the fake crystal properties go away. You know, won't act like a perfectly periodic system because it will magnify in the inhomogeneities. But you also mentioned electron phonon interaction.
Yeah, so that's the dynamical part of the
yeah. And, you know, so I don't think, you know, for most of these things, it's phonon waves that have a wavelength, which is a Moiré period or so, that are most important.
Yeah.
And those waves, of course, have their, you know, their own band structure, so to speak. But I don't think that the gaps in those band structures are big or anything. So, for example, I can't imagine that this is very important for, you know, especially in bilayer graphene, where these effects are relatively small. I don't think it's important for something that sees the lattice vibrations macroscopically, like a resistivity, which is looking at a bunch of phonon modes. I don't think there's any appreciable effect.
Right. Okay, great. Yeah, thank you very much. So let me ask one more time, are there other questions from our viewers out there in internet land? And if not, let us thank Allan again for this really excellent series of talks. And we will convene, at least most of us, tomorrow, Saturday. So thank you very much, Allan.
Okay, thanks, Andy. Thanks, everyone who listened. Thank you. Bye-bye.
Bye-bye.